Hello everybody. Today we begin our first series of lectures on Algorithms 1 course, specifically on Algorithms Design. This is the first of a set of few lectures on Introduction to Recursive Formulations for Algorithm Design. Algorithms and programs are slightly different. Algorithms and programs differ in the sense that a program is typically written in a particular programming language and has a very formal syntax. Algorithms have a semi-formal syntax and are written in a structured manner to succinctly describe the process of the algorithm. It looks very similar to a program, but may not be in any particular programming language. That is why when we write algorithms, we use what are called pseudocodes. A very important statement in computer science is algorithms plus data structures equals to programs. And we shall understand what algorithms and data structures are with respect to our algorithms design course. Now, if we go on expanding what algorithms is, that means if we go on trying to expand out the notion of algorithms, then we will see that this algorithms forms these three steps in the way we will study the algorithms. That is, we will define an initial solution or a set of initial solutions, then we will analyze them, then we will refine these solutions and then add data structures. Now, how will we define these initial solutions? The method that we shall use in this course and in this series of lectures is to use what are called recursive definitions. So, we will use a problem decomposition technique to define initial solutions. And we shall see several examples by which we can do this. The advantage is that these recursive definitions lead to inductive proofs and recurrence equations for their complexity analysis. The complexity analysis of any algorithm is done for two measures. One is called time complexity, the other is called space complexity. These are the two complexity measures which we shall use for our algorithm design, and we shall study the notions of measurement of time and space complexity in more details in subsequent lectures. Then we shall see how this solution that we have defined initially can be refined by understanding how the recursive definition unfolds and how we can traverse it efficiently to form our efficient algorithms. Data structures are used to store past computation in a manner that it can be effectively reused without the need for recomputation. We shall study a large number of problems in this course, and some of them are listed here. The first few appear trivial, like finding the largest and smallest at the same time, the largest and second largest at the same time, or Fibonacci numbers, or searching for an element in an ordered list, sorting, pattern matching, various kinds of permutations and combinations, layout, routing. And in practical problems, we shall see several practical problems which lead to algorithms for shortest paths, algorithms for layout, algorithms for finding various kinds of structures, connectivity, etc., etc. And in order to understand an overall methodology for this program, we shall therefore use this whole concept of recursive definitions. That is why this section is called Recursive Formulations for Algorithm Design. So in order to understand the methodology informally, we shall go through some simple examples to understand how we shall solve the problem. The first problem that we shall take is the problem of finding the largest of a set of integers. So we have a set of integers L, x1, x2 up to xn, where xi is an integer, and let us assume it's a positive integer for the time being, and we want to find the largest. All of us know that there is a straightforward algorithm to find the largest of a set of integers, and that we can do is to initialize a tentative maximum as the first element, and then compare this maximum with every subsequent element, and then determine whenever somebody is better than the maximum, we update the current maximum. At the end of this temporary maximum is finally the largest of all the numbers. Let us now see, for our approach of a recursive definition, how we would define this in a recursive manner. So let us try to write such a recursive definition. So let us try to write max, a definition of max. So we'll write a function max L, where L is equal to x1, x2 up to xn. We will assume x is non-empty, and whenever we write any recursive definition, then what we have to first do is write what is called the base condition. So the first base condition we check is if we check if the size of L is equal to 1, then all we do is return x1. This is the base condition. The recursive condition is that we create a new list after removing the first element. So we create L dashed by removing x1 from L dashed. Then we find recursively the maximum of L dashed, and then we compare x1 with L dashed. So we say that if x1 is greater than equal to y, which is the value returned from L dashed, by calling L dashed it recursively, we return x1, else we return y. So this is the pseudocode form that we use for writing our algorithm, and as you can see that this pseudocode form is the way we will start writing our algorithms. So let us see how it works. It is identical to that sequential algorithm that we just mentioned, which we typically do in a for loop. So let us say we have an initial set of elements 5, 8, 3, 1, 2, 6, and 12. Then what would happen is that 5 would be taken out, and it would recursively call it on 8, 3, 1, 2, 6, 12. Then 8 would be taken out. Sorry, here 5 would be taken out. Here 8 would be taken out. And it will again recursively call it on 3, 1, 2, 6, 12. And then 3 will be removed. And again it will call it recursively on 1, 2, 6, 12. Then 1 will be removed. It will call it recursively on 2, 6, 12. Then 2 will be removed, and it will call it on 6 and 12. Then 6 will be removed, and it will call it on 12, and 12 is our base condition. And as soon as we reach the base condition, the recursion terminates. This returns 12. Now 12 is compared with 6, and then this returns again 12 based on this condition that is given here. Then again from here 12 is again returned. This is compared with 3. This returns 12. This is compared with 8. this returns 12, this is compared with 5, and this returns 12. And so finally, the answer to this is 12. Now, in order to analyze the time complexity of this program, we notice that we will look at the time complexity in terms of the main operation that typically defines this, which is this comparison operation. And as you shall see that for 7 elements, there are going to be 6 comparisons. And these 6 comparisons can also be done through a recurrence equation where we say for any length n, the number of time steps that this algorithm is going to run is equal to Tn minus 1 because of the recursion, plus this one comparison that we have if n is greater than 1 and is equal to 0 if n is equal to 1. So this solution to this leads to saying that this algorithm will require n minus 1 comparison steps. So this is how we start our methodology, by trying to see how we can get a sequential algorithm in a recursive form. However, now once we look at it, now we shall see why this recursive form enables us to get a larger solution space. So we had split this by removing x1 from L, but we could do this separation of L into 2 parts in many ways. So based on the number of ways in which we can do that, we are going to now write a more general recursive definition, which will start giving us an idea of how we want to really develop our algorithm design paradigm. So now we start writing a more generic recursive definition for this problem. That means let us try to write a max 2 L, and let us assume L is equal to x1, x2 up to xn. So this is what L is. Our base condition is the same. If size of L is equal to 1, return x1. Now we say that instead of splitting L by x1 and the rest, we can say split L into 2 non-empty sets, L1 and L2. So now what we have done is that instead of defining an explicit split, we are giving a generalized split, and we are splitting L into 2 empty subsets, L1 and L2. They are disjoint splits, that they don't contain any of their, so they just split it. And then we recursively find out y1 equal to max 2 of L1, y2 equal to max 2 of L2, and now all we need to do is compare y1 and y2. So if y1 is greater than equal to y2, return y1, else return y2. As you can see, what we have done is that we have now split it into 2 parts, of which our previous algorithm, which split in x1 and the rest of it, is a special case. However, such an algorithm can easily be proved. So if we want to get a proof, we can do a correctness proof by induction. we can inductively prove that this algorithm will do it correctly, where we have this as the base condition and these two are the inductive conditions. And we will assume that for sizes smaller than n, it is done correctly. For case equal to 1, it is done correctly, and by the inductive argument, it can be shown that this will yield the correct result because of this comparison that we are doing. So let us quickly see how this algorithm runs now on a special on the same example for any split. So let us see. So let us split it up. Let us again get our same example. And let us split it into two parts. Now we split it into two parts. This again we split into two parts, and I am choosing some sort of a split. This I split into two parts. This is now split into two parts. This is the base condition, single element 3. This is split into two parts. And it goes on getting split till we reach singular elements. And then once we reach a base element, which is a singular element, now this returns 5, this returns 8, this returns 3. Now 5 and 8 comparison returns 8. The comparison here 8 and 3 returns 8. On this side this returns 1, this returns 2. Here again a minimum is done, so this returns 2, this returns 6, this returns 12, so this returns 12, so this returns 12, and finally comparison between 8 and 12 returns 12, and you get the answer 12. You can try and see doing any other split, and whichever split you do, you will also get 12. Now let us see how many comparisons we have done. The base conditions, here are all the base conditions. There are no comparisons here in these base conditions. But in all the other non-base conditions, we have one comparison each. And you can see the number of non-base conditions that arise here are 1, 2, 3, 4, 5 and 6. So we do 6 comparisons. And how do we analyze that here? We write down the time complexity as a recurrence relation, and we can easily write down Tn. Since we are splitting it up into two parts, let us say we split it up into two non-empty parts. So one will be Tk plus Tn minus k, where obviously k is less than n for n greater than 1, and it is equal to 0 if n is equal to 1. And you can prove easily by induction or by any other method that the solution to this is also n minus 1. Which means that whichever way you split it, you are going to get n minus 1 comparisons. This tells us that though we have got so many alternatives to split, we will only do this, we will only get 6 comparisons for these 7 elements, and we will do it with n minus 1 comparisons, and therefore our optimal choice of split could be anything. If our objective is to find only the maximum of n numbers, then we can split it in any way, And since we can split it in any way, our original choice here of splitting into 1 n minus 1, which we have got here, is good enough for us to work out what we have to do. So we can say that for this algorithm, this is the any split is good. So we would prefer to split it into 1 n minus 1 because that is easy to code into a simple iterative loop. So again, the correctness proof, because it is here, we do the correctness proof by induction. We know the base condition. The base condition is for n equal to 1 and the base condition is known. And what is the inductive condition? The inductive condition is that we know that if Tn, that is whatever, let us say Fn, that is the function or the max n, let us say our function is max n, max 2n actually. So let it be written properly. Our function is max 2n. So max 2n, and we know that it is true, inductive condition, that it is correct, it finds it correctly for all n less than n naught. So if it finds it correctly for all n less than n naught, then we can prove from this condition here that if it has found it correctly for this one, if it has found it correctly for this one, then this comparison is enough for it to find the correct answer. So once we know it is true for n naught, we prove inductively it is true for n naught plus 1, and therefore it is true for all n greater than equal to 1. And how did we do the complexity analysis? We just saw we did the complexity analysis by using what is called a recurrence relation. And this, I'm sorry, the recurrence relation was Tk plus Tn minus k plus 1. And here, like here it was Tn minus 1 plus 1, here it is Tk plus Tn minus k plus 1. So it will be Tk plus Tn minus k plus 1, which is this plus 1 is this comparison of y1 greater than equal to y2. And this is for n greater than 1, and it is 0 for n equal to 1. And you can substitute Tk, T, so you can substitute Tx equal to x minus 1, and in this equation you will get Tn is equal to k minus 1 plus n minus k minus 1 plus 1, which will yield n minus 1. So you can also do an inductive proof for showing that it will require n minus 1 comparisons irrespective of whichever approach we use. Now let us see another way of looking at how we solve this problem or visualize this problem. So we are given elements 5, 8, 3, 1, 2, 6, 12. Let us assume that this is like a knockout tournament, and we are going to play a knockout fixture to decide the winner, and the winner is done by a match called comparison. Every pair, so let us say we have got these elements, and we want to have tournaments or matches amongst them. So we could play 5 against 8, and whoever wins, we will play this person against this person against this person, and so on and so forth. We could, so here are the numbers, but here in general it could be x1, x2, x3, x4, x5, x6, x7, x8, and we could define a fixture. Let us say we play these two, then we play these two, then we play these two, then we play the winner of this with this, we play a winner of this with this, we play the winner of these two, then we play the winner of this. So we define a tournament or a knockout tournament, and each point of the knockout tournament is a comparison. And the complexity is determined by the number of matches played in the tournament here, which is these intermediate nodes. And you can show that any way you generate a tournament, if there are n players, you will require n minus 1 matches to determine the winner, whichever way you fix up the tournament. And you can fix up the tournament by this, or you could fix up the tournament by creating some other mechanism. You could create some other mechanism. You could make x1 play with x3, x2 play with x4, x5 play with the winner of these two, and then you could make a tournament in any form you want to declare the winner. You will end up with this. So this is another way of visualizing this, and I will explain to you later on why we are using this method of visualization. So by this approach, we have solved a very simple problem. Just for understanding what we wanted, we took the approach of trying to find the maximum of n numbers. We got a sequential recursive definition. Then we got a more generalized recursive definition. Then we analyzed that recursive definition by a recurrence equation. We gave an inductive argument or a proof for it. We did a complexity analysis, and we found that whichever way we split, all of them give the same solution. This being a trivial problem, the method is not trivial, as we shall see in the next example. So our next example is that we have to simultaneously find the largest and the smallest of n numbers. So if we have to find the largest and the smallest of n numbers, then when we typically write a program, what do? We initiate two variables, max and min, and we initialize max and min to the first element x1, and then compare it sequentially with every element. If that element is larger than the max element, then we update the max. Otherwise, if it is smaller than the min element, we update the min. Let us write that down in the same recursive formulation that we did now to understand how to do that recursive formulation. So we now write it down. So we write max min L. And what we say? We say let L equal to x1, x2 up to xn. Again, our base condition is if L is equal to 1, there is only one element. Please note that this will return two elements, the max element and the min element. And suppose we first return the max and we return it in a pair of max and min. Because here there is only one element, it will return like this. Otherwise, which means that if L is not equal to 1, then in our sequential mechanism we follow the same thing that we did before. We do minus x1. And then we recursively find out y1, y2, which is the max and min, which comes from L dashed. And after we have found the max and min from L dashed, we now compare. What do we compare? We check if what is the status of this value. So what we now compare is we compare this with x1. So if x1 is greater than or equal to y1, then we say then m1 is equal to x1, else m1 is equal to y1. On the other hand, if x1 is less than equal to y2, then m2 equal to x1, else m2 equal to y2. Which means that from these two which are returned, if x1 is greater than y1, then x1 is the largest, otherwise y1 is the largest. On the other hand, if x1 is less than or equal to y2, then x1 is the smallest or y2 is the smallest. So if that is the case, then we now return m1, m2. Let us now see how this algorithm works with our previous example. So our previous example was 5, 8, 3, 1, 2, 6, 12. So in this example, we first take out 5 and we recurse on the rest. Then we take out 8, we recurse on the rest. Like before. We are doing all this just to give you an idea of how the method works and how the method is subtle enough to capture many things which will help us design algorithms. So here is the base condition which is 12. And now since we have reached the base condition, we now see how the recursion returns. So unlike the previous one, here two values are returned. So this returns 12, 12. Now 6 is compared with 12, and therefore m1 is 12. Again 6 is compared with 12 and m2 is 6. Because here in the first case 6 is not greater than 12, therefore m1 is 12. But here 6 is less than equal to 12. So this returns 12, 6. Then again 2 is compared with 12 and 2 is compared with 6. And this returns 12, 2. Similarly, this will now return 12, 1. This will return 12, 1. And this will return 12, 1. And then with 5, the final result is 12, 1. As you can see that the final result is 12, 1. And how do we do this analysis? In order to do this analysis, we will now go to first our recursive definition. And just to understand the analysis here, please note that whenever there is one element, so our complexity analysis turns out to be that Tn is equal to 0 if n is equal to 1. Because if there is only one element, then you don't need any of these comparisons. Otherwise, it is equal to Tn minus 1 plus 2, because we are doing two comparisons, one here, one here, if n is greater than 1. So this is our recursion here, and you can easily see that this will yield our number of comparisons. Tn will end up with, the answer of this will be, Tn will be 2 of n minus 1. So it will become 2n minus 1. That is the complexity here. As you can see, here there are in 6 intermediate nodes for these 7 elements, and therefore there are 12 comparisons, 2, 4, 6, 8, 10, 12. Now let us see if we go to our recursive definition. How will we do our recursive definition? Our recursive definition will be in the same lines that we did the previous one. So we will now write max min 2L. Let L equal to x1, x2 to xn. Interestingly, we will now have the same approach, which we will do now, is that we will check whether we are going to split, what are going to be our base conditions here. What are going to be our base conditions here? We know that if L is equal to 1, then we return x1, x1. On the other hand, if there are two elements, then by one comparison, we can find out the maximum and minimum for two elements. So we have another base condition. If L is 2, then we do one comparison. What is the comparison we do? In this case, if L is 2, we do the comparison if x1 is greater than equal to x2, return x1, x2, else return x2, x1. So if x1 is greater than x2, then max is x1, min is L2. Otherwise, max is x2, min is L1. So we have got our two base conditions. Now we do our recursive condition. Split, same approach we used in the largest, L into two non-empty sets, L1, L2. We split it into two non-empty sets, L1, L2, and recursively get y1, y2 from max min 2 of L1 and z1, z2 from max min 2 of L2. That means y1 is the max and y2 is the min of L1, z1 is the max and z2 is the min of L2. Now it is easy for us. We now need to compare only y1 and z1 and y2 and z2. So for us, if y1 is greater than equal to z1, M1 equal to Y1, else M1 equal to Z1. If Y2 is less than equal to Z2, M1 equal to Y2, else M1 equal to Z2. And we return M1, M2. So what have we done? We have had two base conditions. One is if there is only one element, then we return x1, x1. If there are two elements, then we compare x1 and x2 and accordingly return the max and min. Otherwise, if there are more than two elements, we split it into two non-empty sets L1, L2, and we return the max min of L1 and the max min of L2. We compared the two maxes to determine the maximum, and we compared the two mins to determine the minimum and return the maximum and minimum. Here again, it is easy for us to show by induction that this will work, and it is also not difficult for us to do an analysis of this. So let us quickly run through an example, our old example that we had. Let us run through using that example. So our example was, we had a list which was 5, 8, 3, 1, 2, 6, 12. These 7 elements. Let us say we split it into 5, 8, 3 and 1, 2, 6, 12. Again, this one we break it up into 5, 8, and this one we break it up into 3. This one we break it up into, let us say, 1 and 2, 6, 12. This one, 2 elements is a base condition, 1 element is a base condition, 1 element is a base condition. This is not a base condition. So let us say we split it up into 2, 6 and 12. Now each of these are base conditions. And getting each of these as base conditions, we now start seeing what values are returned. This will return 8, 5. This will return 3, 3. This will return 1, 1. This will return 6, 2. This will return 12, 12. So this will return 12, 2. This part 5, 8, 3, 8, 5 and 3, 3 will return 8, 3. This part will return 12, 1, and finally we will get 12, 1. And it is not difficult to show by induction how many comparison steps are there. Now let us see how many comparisons have happened here. So let us see. The number of comparisons in singleton sets is all 0. Comparison in pairs of sets is 1, because we need one comparison when the L set is size 2, and we need 2 comparisons when it is more than 2. So here we need 2 comparisons, here we need 2 comparisons, and here we need 2 comparisons. And here we need 2 comparisons. So total number of comparisons is 1 plus 1, 2 plus 2, 4, and to 6, to 8, 10. So we require 10 comparisons. On the other hand, if you observe very carefully, you will notice that for this branch of the tree, for this branch of the tree, we required 1 plus 2, 3 and 2, 5 comparisons. If we had split this part of the tree in a different way, that means we split 1, 2, 6 and 12 as 1, 2 and 6, 12, then we would have got the same answer, because this would return 2, 1, this would return 12, 6, and this would return 12, 1, which is the same as the return value out of that block. But if you notice, the number of comparisons this will require 1 comparison, this will require 1 comparison, and this will require 2 comparisons, which means that this block, by a different split, will require a total of 4 comparisons, whereas this block had required a total of 5 comparisons. And therefore, if we use this split, the second split, instead of the first one, then the total number of comparisons will no longer be 10. We can do the whole thing by 9 comparisons. Now we see that there is a difference between finding the largest and finding the largest and the smallest, which shows us that every split is not the same as in the previous case. In this case, the splits are different. Let us analyze this a little more. There is a slight typographical error in this, so I just a typo where in the first sentence here, if y1 equal to z1, m1 equal to y1, else m1 equal to z1 is fine, this should be m2. So just we should make this correction before we proceed. So let us go back to the choice of split. We have seen that the choice of split, whenever there are 4, 6, 7 elements, let us say, if there are 7 elements, we can break it up into 3 elements and 4 elements. And these 4 elements can be broken up either as 3 elements and 1 element, and this can be broken up as 2 elements and 1 element. Here these are not values, these are the number of elements in the array, in the list. So if we do this, we already know that the number of comparisons for 2 elements is 1, for 1 element is 0, 0, for more than 2 elements is 2. Similarly, this 3, 1, 3 elements, everywhere which we do 3 elements, again here, this will be broken up into 2 elements and 1 element, and therefore the number of comparisons here will be 0, number of comparisons here will be 1, here 2, and here 2. So again this side is similar. We have got 5 comparisons, just like we got in this case where there were 4 elements and we split it up. On the other hand, if these 4 elements were split up, these 4 elements were split up differently. If these 4 elements were split up as 4 was given 2 and 2, then we would see that we will require 1 comparison here, 1 comparison here, and 2 comparisons here, leading for this block to be done in 4 comparisons here instead of the 5 comparisons here. So there is an optimal choice of split. And how do we determine what is that choice of split? So we would like to see that in this decomposition, we would like to ensure that we minimize the number of nodes which have got 2. And it is not difficult to see that we could, if we split it up always, if we have n elements, and we always split it up as 2n minus 2, then we will yield an optimal solution. How? Let us write down the generalized recurrence relation. The generalized recurrence relation is Tn is equal to 0 if n is equal to 1, is equal to 1 if n is equal to 2, and is equal to tk plus Tn minus k plus 2 if n is greater than 2. If we split this k as 1, if we choose k equal to 1, then we will get T1, which is 0, plus Tn minus 1 plus 2, and it will yield us to a solution of 2n minus 1 as we saw before. On the other hand, if we choose k equal to 2, then we will break it up into T2 plus Tn minus 2 plus 2, which if you decompose a little more carefully, you will see that this will now break up into a more interesting solution. What will happen to this solution if we break it up? Then, since it is breaking up into 2, so it will be T2 plus T2 plus Tn minus 4 plus 2 plus 2. And if you try to solve this on your own, you will see that the answer to this will be very interesting. The answer to this will be 3n by 2 minus 2. And this 3n by 2 minus 2 is definitely smaller than 2n minus 1. Therefore, this would yield a much better optimal solution. So we know that choosing k equal to 2, split it up into 2n minus 2, always yields a much better solution. There is an even more general way of looking at it, and we shall see how that happens. So now we see the advantage of our tournament-based analysis. Our tournament-based analysis. So our tournament-based analysis, let us go with that same example for our tournament-based analysis. In order to do our tournament-based analysis, let us look at 5, 8, 3, 1, 2, 6, 12. We could compare these two. We could compare these two. We could compare these two. We could compare this. We could compare these two. Maybe we could do this instead of doing. One was the 2n minus 2. I have given a different option. And what would be the result coming out from here? This would yield 8, 5. This would yield 3, 1. This would yield 6, 2. This would yield 12, 12. This side would give 12, 2. This side would give 8, 1, and this side would give 12, 1. How many comparisons? This step would require one comparison, 1, 1, 0, 2, 2, 2, which is again 9 comparisons. Which is the same as 3 by 2n minus 1, taking the integral value of this, because there are 7 elements. So 3 into 7 by 2 minus 1, sorry, minus 2. 3n by 2 minus 2. So minus 2. So this would yield 11 minus 2, which would be 9. Now, as we can see from this, that this is not the 2n minus 2 split. So is there a more generalized method of trying to determine what is the optimal split? And as you can see, by doing a little careful analysis, if we want to look at the generalized optimal split here, and we shall study these tournaments and its analysis in a little more details in subsequent classes. But if you analyze this in a little carefully, what we shall see is that our optimal split would be if the size of L is even, then split into even parts. That means if it is 4, then don't break it up into 3, 1. Break it up into 2, 2. This is better than 3, 1. And if L is odd, then split into even, odd. And I leave it to you to think. For example, suppose you had 6 elements. You had 2 choices. One is you could split it up as 3, 3, or you could split it up as 4, 2. If you had got 26 elements, you could split it up as 13, 13, or you could split it up as 10, 16. So the more generalized split is, if it is even, split it into even parts. If it is odd, split it into odd even parts. And you can prove that this will always yield you the optimal 3 by 2 n minus 2, the integral part of it. This is how the integral part of it is written, and you will get the solution. And I leave it to you to prove that this is the most generalized split. So the reason why we did a tournament-based analysis is to find out how the tournaments form. And we shall see that there are even more intricacies to such tournament-based analysis. So in this first lecture, we have begun our study of algorithm design, where we have shown how recursive definitions can be used as initial solutions, and from which we can then examine in more details to find how we can refine that solution and find optimal points. We also briefly saw how recurrence equations for both for proofs as well as for time complexity analysis can be done in order to analyze these initial recursive definitions. And we saw that these recursive definitions go through this concept of a split, and how we can devise such a split in a generalized form, analyze the split, and then determine what is the optimal split and that was our solution refinement technique. Later on, we shall see even more details in other examples. We have done only the first two sample problems, the largest and the smallest, whereas in the largest we found that every split is of identical complexity, but when we did the same thing for the largest and the smallest, we noted that all the splits are not of the identical complexity, and there are some splits which are better than the others, and that is why, choosing that appropriate split, we got an algorithm that was at least a little faster than the base algorithm. We shall continue our discussion on more examples in the subsequent lectures of this part of algorithm design's initial examples, where we will look at recursive definitions and what are the ways in which we can transform these recursive definitions. Thank you very much. Please share any questions that you may have, and we will